welcome to our workshop, which is part of the Hamlin Symposium on Medical Robotics. Our workshop is entitled Soft, Smart, Functional, Agile and Aware Surgical Robots, and we will be focusing on progress and technologies. For those of you who have been here already yesterday and the day before, you know that this is a three-part workshop. And so we are doing this workshop over 3 days. And we had already some very exciting presentations in the area of soft robotics for medical applications. And we will continue today with with a third part, concluding part. And I look forward to some very exciting presentations, which will be today. So today the focus will be on modeling, learning and control of soft robots. And I see that all speakers are already here, so that's fantastic. My name is Kaspar Altöfer, I should say that maybe as well. And I'm joined by Panos Kasanos as co-chair, as well as Helge Wurdemann. So we will share the session today. And again, fantastic. Thanks for joining. We have already 32 participants coming in, but I'm sure these numbers will go up while we move forward. So really, this workshop is interested in exploring the idea of soft robotics for medical applications. And so we looked at actual implementations of these systems and looked at the actuation of soft robots in the medical field, but we also had the opportunity to hear about the newest achievements in sensing, soft sensing, in the context of soft robotics for medical applications. And today we have the great opportunity to look now at modeling, learning and control of these soft robotic devices in their medical environment. And as I said, we will have 4 fantastic presentations. I would like to highlight a few additional points. Every speaker, if I could ask you please to stick to maximum 25 minutes. That would give us then per presentation another 5 minutes for discussion. If you keep it even shorter, even better. I would even prefer to have even more time for discussion. But after half an hour, unfortunately, we have to move to the next speaker. We also have posters and Panos will send you the link, or has done that already, in the chat. And that brings me also to the chat. So you have this Q&A system there. Please do submit your questions there. Then we can take them forward to the speakers when they have concluded their presentation. I think that is a very useful tool to get the discussion going. I think I mentioned all the points I wanted to mention, unless I forgot something. Nope, my co-chairs are happy. Then I would say, without further ado, we'll move to the first speaker, and it's really a great pleasure to have Darwin here, Darwin Coldwell from the Italian Institute of Technology. And really fantastic. Thanks for joining us. I've been working with Darwin for many years, and we had the fantastic collaboration in the StiffLab project. So I'm now really keen to see where he is heading with his current work, and really interested to hear more about the 5G robotic telesurgery. Darwin, great to see you here, and the floor is yours.
Kaspar, thank you very much. Can you see my screen and hear me okay?
Yep.
Okay, thank you very much, Kaspar, for that introduction, and thank you for the opportunity to come here. Yeah, my topic is 5G telesurgery, which is a little bit out of soft robotics, but I hope the robots are agile and advanced and everything. And I hope people will actually get something valuable from the presentation. This is some work which is done in our biomedical robotics lab at IIT. That lab is led by Dr. Leonardo de Matos, who's in the bottom left. And you can see him with his team. These are some of the guys who actually have been put together aspects of this work, and so need to really say special thanks to them, and also particularly to Dr. Alper Achimoglu, who's been very involved with the 5G work. So just to give you a little bit of an outline on what I'll be talking about, look at telesurgery, what it is and why we might want to do this. Maybe we're all very familiar with this, but I'll give you some background on my thoughts on that just to get started. Then I want to look at transoral laser microsurgery. Transoral laser microsurgery is an aspect of surgery which we've been looking at for several years now. Microsurgery is very suited to aspects of telesurgery. And so I want to look at the robotic systems we developed in this because they are key to how we do the telesurgery. We'll look at the CAM system, that's a computer-assisted laser microsurgery, how we integrate that with an exoscope, a commercial exoscope from Storz, and then look at some robotic microforceps that we've been developing again in the context of the telesurgery. Then go on to look at the 5G telesurgery setup and operations. So look at the surgeon side console, the patient side console, and then some safety protocols, which are of course essential to any aspect of teleoperation. Look at the experiment itself, what we are actually going to be doing. As I said, this was one of the first, maybe the first example of a 5G telesurgery. And then we have some results from that and some final conclusions. So just looking a little bit at telesurgery, what is telesurgery? Well, it's surgical procedures carried out at a distance. That is essentially the essence of telesurgery. It relies on advances in robotics. It relies on advances in haptics, in communication, in augmented reality, virtual reality, many other types of AI computer technology. It is real-time information flow in both directions, from the surgeon to the patient and back from the patient to the surgeon. And this has to be done in real time or as close to real time as possible. We actually want to look at it. Why do we use telesurgery? Well, there are several, considered to be several good reasons why we want to be looking at telesurgery. The first is for urgent interventions. When you have an emergency situation, a life-threatening situation, it may be impossible to move the patient or the surgeon or move them fast enough to be able to save life. And so telesurgery would allow that to take place. We want to do it for rural and remote environments. So if you're somewhere distant from the hospital, it may be impossible to move the surgeon. It may be too expensive for the patient to actually come in to actually do the operation. And it can be for very extreme remote environments. So this could be to ships at sea, to people at the North-South Pole, and even into space, where we want to do these operations. Big area that's sort of falls a little bit within the telesurgery is collaboration and training. Whenever you have the aspects, in first world countries, you have best facilities and the best surgeons and the best training. But with telesurgery, what you're able to do is offer those facilities and those educational opportunities to people around the world, so that they can participate really effectively. You have the precision which comes with the robots. So in telesurgery, you almost always have a robotic system, and the robotic system typically would give you greater precision, better quality than you would get with the normal operations, the normal surgery. And this is particularly true when the operation is very complex. So when you have something which is very delicate, when it's very small, or when you have a new surgeon who doesn't have so much experience. And so what you can actually do with the robotic system, you can add in systems to increase the safety. And then finally, this potentially leads into more automated surgical procedures. So not automated surgery as such, but as a stepping stone along the way to automated surgery in the future, but also maybe even just looking at certain aspects of the process. Now, we've all know, telesurgery and robotic surgery, there's a lot of overlap. If you actually look at many of the systems, the Da Vinci systems, the Versus systems, etc., you will realize that what we call robotic surgery is also in some aspect telesurgery. The difference is that with the type of robotic surgery, we're talking about a distance between the master console, the surgeon, and the teleoperating patient of a few meters, 5-10 meters absolute maximum. And so there's a relatively small distance, but they still are dislocated from each other. And so what you want to do is the master station wants to transmit manipulation commands, audio stream. You want to feed back high quality video, maybe high quality audio, vital signs, haptic feedback. With the telesurgery, and what we want to look at the most advanced aspects of telesurgery, we want to move those meters of separation to kilometers, and maybe ultimately to tens of kilometers, perhaps even further. And so that's the key. What actually happens when you go from being a few meters apart with a wired connection to tens of kilometers apart where maybe there is no wire connection? And if we actually think back, when was the first telesurgery? Well, the first long distance, first transatlantic telesurgery was 20 years ago, 2001, the Lindbergh operation. This was a surgical procedure between surgeons based in New York and a patient in Strasbourg in France. And they actually used a dedicated fiber optic communication. So it wasn't wireless, it was a dedicated line just for this communication, fiber optic to ensure very high speeds. It had a fixed latency, so there was no variation of 155 milliseconds, and it was essential that they had no packet losses. And so these were all vital criteria, and they still are vital criteria. These types of things are still vital. But given that it was 20 years ago that we did this, what has happened to telesurgery in that intervening time? Well, by and large, we have robotic surgery, as I said, but telesurgery hasn't really taken off. And that's because of the high communication cost, because of the long latency. So in the Lindbergh operation, there was a fixed fiber optic with a fixed latency, but typically the latency is variable and the latency can be quite long, and that can make control very difficult. And it also even can induce a form of motion sickness for the surgeon, where his eyes and his physical motions are not connected to each other. And then you have the idea of being able to guarantee reliability on a public internet. So the Lindbergh operation used a dedicated line, but when you have a public internet, there are safety issues and there are also legal issues, as in if something goes wrong, who is responsible? And when we move to 5G, what's the advantage of 5G? What is it? Why do we benefit from it? Well, first thing to actually point out is 5G is not just an evolution of 4G or 3G. It's not just a simple transition. It actually has many distinguishing features, major distinguishing features. It's an ultra broadband. It has up to 10 gigabits per second, very, very high data speeds. It's ultra reliable, ultra low latency, down potentially to 1 millisecond. That's very difficult to achieve, but it has still very, very low latencies. It's massive connectivity. You're able to connect 1 million devices per square kilometer, phenomenal amount of connection. You have a quantity of service which is guaranteed, which is ensured by multiple input, multiple output antennas. What does that mean? It means that we're able to direct the power, to direct the resources to exactly the point that the user wants them to go to. So it's directionable. We can use it. All that power, we can direct it to where we want to go. We have an infrastructure which is built on virtual networks, virtual network elements. What do these do? They ensure flexibility and resilience. Again, being able to rely on the safety of the system, being able to guarantee that things will continue to work when potentially something unexpected happens. Then we have aspects of network slicing. We want to create these virtual networks with specific characteristics, with security characteristics, with traffic routing characteristics, with quality of service characteristics. And we can do that using the network slicing. We can then further customize that service for specific applications and for specific users. So we can have a dedicated allocation of resources to safety critical services. And that's what is so important for telesurgery, because we can guarantee that there is a safety critical operation, and that will guarantee the network for that behavior. Now, I want to look, so having given you a little bit of background on telesurgery, I want to look at why we want to look at this transoral microsurgery. And so this is the setup. This is a current state-of-the-art setup. We work with Dr. Giorgio Peretti at the San Martino Hospital in Genoa. And here we can see Dr. Peretti doing a typical vocal fold operation. So what we actually have, this is operations on the vocal cords at the back of the throat. And see, we see a close-up of this system. These are the vocal cords. These are typically 10 to 20 millimeters in length. Very small structures, very easily damaged. Any damage to them during the surgery will cause a change in voice, which actually has important psychological impacts. And what we can actually see is we have the setup. So we have Dr. Peretti. He uses a microscope because the area is so small. He operates through using a laser, a CO2 laser, which is external, and then is guided through a series of optics. And here we can actually see a close-up. So we have a series of optics built in here, which are physically manipulated. So you have a joystick, like the joysticks you have on gaming consoles, maybe less sophisticated than the joysticks on a gaming console. So you have the joystick, which physically moves mirrors. And by moving the mirrors, you're able to steer the laser beam. Laser beam is directed into the mouth cavity of the patient through a laryngoscope. This distance is about 400 millimeters. It's quite a long distance. And what you end up with is you want to get millimeter precision over a long operating distance. The surgeon's hand is here. The operating site is quite a long way away. So any motion here is massively amplified. You have very poor ergonomics during this. You can see the actual position. The surgeon is sitting a little bit hunched over to be able to see the microscope with the arms up and raised. And I have that they has them on a chair, but still they're up and raised. And he will be doing this for long periods of time. So it's a lot of pain in the back, a lot of pain in the neck, a lot of pain in the arm. So it's poor ergonomics combined with controlling of a foot pedal, which we see down here. So there's a hand-eye-foot coordination. There's poor controllability. By that, I mean, it's very difficult to control the motion of the joystick here to get very small motions on the operating surface. Visualization is difficult. Here you can actually see the laryngoscope. It's about 10 to 20 millimeters across. You're introducing a variety of objects in that. You have a manipulation tool. You may have an airway. It's a very small area, very difficult to actually get a clear view through it. And the access, of course, is very poor as well. So what we wanted to do was to try and automate this, to try and improve this process to make it better for the surgeon. And so we created the CAM system, the computer-assisted laser microsurgery system. And here you can see some aspects of that particular system. So this is Leonardo, who leads the lab, as I said. And he's using a conventional microscope, but he could use a virtual microscope, in which case he's able to feed back augmented images. So we can feedback, we can show spatial information, we can augment that information, we put virtual information to provide him with additional data. He works through the microscope as before, but here, what we've actually done is the joystick and internal optics have been replaced by essentially a robotic system. It's a series of fast steering mirrors, which are automated and motorized to be able to provide this laser, robotic laser microsurgery. We control this from a tablet. So no longer do we have the joystick, we now have an external tablet. So people use this like drawing. There's no need to actually learn. This is something that you've been able to do all your life, been able to color in between the lines. And so the motion on the tablet actually physically controls the tip of the laser. You can see that there is almost no additional materials added in here. So there's negligible impact on the workspace. It's a very clean workspace. We can add in a variety of different other materials. We actually have microscopes. So onto the microscopes, we can actually put cameras. So we can visualize directly through the cameras. We can have haptic devices, which you see here. And again, in this setup, a two-handed haptic device where we can use that either to control the microscope or to control the laser, or in our case, we're using this to control a secondary robot. And you can have all of these additional activities added into it. So This is an example of a test scenario. So this is a small test scenario we set up. We tested this scenario with 150 surgeons. There were actually a large conference in Genoa at the time. We invited 150 surgeons who were visiting that conference to actually use this system. So we managed to get a lot of feedback. And what you can actually see is the surgeon, the tablet system. Occasionally you see a puff of smoke, and this is the vaporization of the tissue. The surgeon actually is manipulating with his left hand. Down here, we can visualize what he actually sees through the microscope, and up here is a larger display. And on the right-hand side, we can actually see the types of tracking you actually get. So this is an example just onto plaster blocks. And on the left-hand side, the two left-hand models, what you actually see is this is a state-of-the-art system. So using the conventional joystick to do it. And you can see there is tracking. The idea is that the surgeon is actually supposed to stay in the S-shaped line. And you can see that they approximately do that. But there's a certain spotting and there's movement outside the line. If you actually go to the right-hand images, what you actually see is very, very high precision tracking. You see it's very, very accurate. So you see that the actual CAM system is able to give that very high precision. But that's not the only advantages you actually have. I said we were able to add augmentation. So here you actually see that the surgeon's wearing a headset, and we can augment this. He uses the traditional tablet that we've been talking about before. In the middle diagram, what we've seen, the blue area is a safety area. So when the laser goes into that area, we've defined that as an area we don't want to make cuts. So when the laser goes into the blue area, it turns off, and it actually turns off automatically. It detects the presence, you see it turns off, no cutting. Right, goes back into the non-blue area. So we can actually define safety areas. So if you were training a young surgeon, what you could actually do is the experienced surgeon could say, this is a dangerous area, don't go near it. If ultimately you decide you want to cut there, you can redefine those margins. Over here, we can actually see, we can actually plan the actual incision. So we use the yellow line to plan the excision, then we use a spotter laser to plan the motion, and then we actually make the cut. And over in the right-hand side, what we see is an ablation. And so what you would see with this area, the area inside red, we've actually highlighted this area. In this area, we want to remove all of the tissue. Now, this would be almost impossible to do with the traditional system where you'd have to move the laser backwards and forwards using the joystick. And to stay inside that area would be impossible. But what we can actually do is we can plan that. And with the robotic system, we will move backwards and forwards, essentially rubbing away as if with sandpaper, the actual surface. So we can rub away the surface to the depth that we actually want to. So these are the types of technology that we can actually integrate into the CAM system. We can then move further because one of the things we needed was high quality images. And so we've been working with Storz using their exoscope, the Phytome exoscope, to be able to produce, so instead of using the microscope, to be able to use an external endoscope. And here we can actually see the images which they project. So these are high quality, these are HD quality images, 3D images, and you can actually get this. So the image you see on the screen here is 3D image when you wear glasses. And so the surgeon actually wears glasses and all the surgical team will wear glasses, and it turns it into a 3D image that the surgeon can operate on directly. And so 2 years ago, we actually did a demonstration, a live demonstration of this procedure using the CAM and the Phytome system. And this was done at the SIO conference in Rimini. And as I said, it was in front of a live audience. And again, Dr. Peretti, so you can actually see him here. He's doing the operation. In this instance, it's not telesurgery. The patient and the patient and the surgeon is cadaver in this case again. The patient is directly in front of the surgeon, but he's able to do the operations. He uses the tablet, he uses the imaging system, he uses the guidance here, he uses the CAM directed system. And so we have all of the actual facilities to be able to do this. On the other side of the patient, one of the things we needed to do was to be able to manipulate the tissue. And we could have used a conventional, we could have used a robotic system, we could have a Vincia versus type system, but we actually developed our own hardware to be able to do this. So we developed a robotic microforceps with haptic feedback. So this is an 8 degree of freedom system providing grasping force and haptic feedback. And we integrate this with the CAM system to be able to provide this level of computer integrated support. What do we want to do in terms of the laser surgery? So what we actually have is we have the surgeon. Now, we actually did, this was part of a process sponsored by the Italian government, but in conjunction with Vodafone in Italy. And so we operated, the surgeon was based in Vodafone Village in Milan, which is in the southeast of Milan. And you can actually see him on the stage here in front of an audience doing the operation. And so we actually have the surgeon in the Vodafone Village. We have the patient. As I said, it was a cadaver, which is actually in the anatomy lab at the San Raffaele Hospital, which is in the northeast of Milan. And we had, at that particular time, Milan was the most 5G network city in the world. And we had the ability to use the 5G network that Vodafone had installed to be able to transmit from one side of the city to the other. And so here we can actually see the type of system that we have in a little bit more detail. On the surgeon side, we have the tablet, which actually controls the laser. We have a haptic device, which we use to control the robot arm, which is a Franca Panda. We have a head-mounted display, which we actually use to display. Could have been a screen, but we used a head-mounted display in this instance. We also had webcam and mic. So we were using basically a teleconference setup, which at the time, 2.5 years ago, was actually relatively, I mean, everybody now uses, this is what we're doing now. So everybody is now so used to being able to transmit. But at those particular times, to have reliable, good quality transmission was a little unique. No, it's a little unusual, but we actually found it incredibly valuable because we actually had a bigger picture of what was going on. On the patient side, we have the CAM system using a DECA robot. We have the Franca system, Franca Panda, with the forceps. We have the Vitum 3D exoscope, which produces high definition images. And again, we have the webcam transmitting backwards and forwards across a distance of 15 to 20 kilometers. And this is the actual physical setup. You have 3D glasses. So the surgeon, the haptic device, which he uses with the left hand, tablet with the right. Different surgeons switch them around left and right. They're equally possible to use. And on the robot side, we have, or on the patient side, we have laser arm, the CAM system, the laryngoscope, the cadaver, etc. Now, in terms of safety protocols, I'll just go through this quickly because time's pushing on. We have a number of different safety protocols. So we have a network safety protocol to ensure integrity in the 5G network. We have a laser activation safety protocol, which means that both on the surgeon side and the patient side, we have to be aware of the fact that the laser doesn't turn on. It doesn't turn on if a surgeon turns it on, it doesn't turn on at the patient side. They both have to agree to do the safety. We have control safety systems to look at timeout. So if we actually lose signals, which it's unlikely to happen, but in case it does happen, if we have this safety timeout, then we will actually shut down all of the systems to actually provide this protection. And then we have, as if most robotic systems, we have local emergency stops. The actual experiments itself, so we had this was actually performed by 2 expert otolaryngologists. Neither of those surgeons had any prior experience of teleoperation of telesurgery. The first surgeon, in actual fact, had no prior experience of robotic surgery in any way, shape, or form. He had 10 minutes of pre-training with the system, and after 10 minutes pre-training, he felt confident enough to actually start the surgery. The second surgeon, he was familiar with the CAM system. He'd worked in the hospital in Genoa, and he'd used the CAM system. So he had used that, but never used it in remote mode. And again, after very short training, he was quite happy to do this. The actual procedure we were following was operation on the vocal cords. So there was initially exposure of the vocal cords, and this was followed by a type 1 cordectomy on the left vocal fold and a type 2 cordectomy on the right vocal fold. As I said, the surgeons were in the Vodafone Village, cadaver in the anatomy lab, and we used a 5G network operating at 3.7 gigahertz. And so this is the actual setup. So here we actually have the surgeons in the hall at the Vodafone Village. You can actually see the surgical site. So this is the view through the laryngoscope using the exoscope. This is essentially the a video conference where we have a large view of the room so that the surgeon is well aware of what's actually going on in the room. This is a very confined, you know, this distance across here is 30 millimeters maximum. This shows him operating in the room, head mounted display. You see here using the stylus, and occasionally you'll see little flashes and sparks. That's the laser being turned on, and he guides the laser with the pen. And then on occasions, what you'll actually see, this is the forceps, and when he moves the haptic device, you'll see the forceps actually moving. So in a second, I think he moves this. Yeah. And so you actually see he's able to physically manipulate and to feel the pulling on the tension on the tissue. So he can actually feel the physical contact with the tissue. And up here, this is the 5G router. So this is just showing other close-ups of the slides, but I'll move on because we're pushing Casper's time. The operation went very successfully from a medical procedure. From an engineering perspective, this gives some of the data. And one of the most important aspects was the quality of the signal. The latency was actually being of the actual process. And so we were sending full 3D, as I said, with a full 3D signal. The mean latency was 100 milliseconds, maximum 140. This is 140 milliseconds. This is the mean here. This is with all the processing. If we remove the processing on the system, it's actually much faster. So there's a lot of slowing down because of the image processing. The control commands, 22 milliseconds is the mean, 30 worst case scenario, and the estimated round trip, about 125 milliseconds, which is actually faster than the Lindbergh operations, if you remember, 170 maximum. We ended up, we got a lot of national, international exposure from this, which was very, very nice. And then just some conclusions. I think I'm on 25 minutes, so I'll try and keep Casper very satisfied. So just some general conclusions. The 5G telesurgery experiment was a complete success. The doctors told us that in actual fact, doing this, they felt as if they were doing it in the operating theater. They did everything pretty much as they would normally do. The time to actually complete the operation was not significantly longer than their normal operation. So they were very happy on that in terms of being a medical output. We demonstrated effective control of the surgical system from a remote location. The surgeons performed high precision laser cordectomies with very low latency rates that meant it was possible for them to do it. It was a full HD stereo visualization of the surgical site. It was exactly the same quality as in the operating room. The response of the robot, we used a very responsive robot control system. And one of the things which I've not really talked about, but was efficient collaboration with the patient side. As I said, the video conferencing, which is now something we take for granted, in those days, yeah, it was still quite common, but they found it very useful to be able to explain things, to see what was going on, to be able to move the images around, to get the bigger picture of the operating room. So what we're looking for is a future of healthcare, 5G hospitals with telesurgery, telemonitoring, patient monitoring, data engagement, data management. And just to thank all the people in the lab, our clinical partners, our industrial partners, engineering partners, and our funding sources. Thank you very much.
Fantastic presentation. Thank you very much, Darwin. This is Helge.
Hi, Helge.
How are you doing? Thank you very much for showing us the advancement that you have been doing in the field of 5G teleoperation. It's always fascinating to see it after 2 months. You have some new amazing work to show everyone. There's a question from the audience by William that I'd like to start with. Can you briefly touch on the Omega haptic device that you have been using?
Okay, the Omega it's the commercial system, so it's a parallel robot. So it's just a normal haptic device, which we use for many different types of operation. We use that to control the tip. So basically, we're controlling the final point and the manipulation of the microforceps. And so we use that for the microforceps. We use the tablet to control the laser because, of course, the laser has we just want to control the laser on and off. But we use the Omega to actually control the physical motion of the Panda robot and the forceps that actually go with it. And it provides us with the control and also with force feedback. We use it in different modes. So one of the things we discovered when we were first working with the surgeons, we turned the scaling down. So it has a scaling factor. to help make the surgery more delicate. You can move in very small areas, and we had a scaling factor, and we turned the scaling down. So they had to move maybe 10 centimeters to be able to move 10 millimeters. And after a while, they said this was too slow, and they wanted this moved up. So there are various different things that we'd actually do, and different surgeons might want different scaling. But yeah, that's the type of system we have.
Thank you very much. And please let me invite everyone to either post questions into the question and answer tool on Zoom, or just raise your hand so that we can listen to yours. Casper, please go ahead.
I just raised my hand physically, if that's okay. No, fantastic presentation. And I have to say, I was not really, so keen on 5G. I said, okay, 5G, just a new gimmick. But I can really see now the advantages there. And I mean, very high speeds and in particular latency is really, coming down and seems to also work in a reliable way. Particularly very important for tactile information, haptics. So I'm wondering, can we just, rely on that is happening, like our computers are getting faster, telecommunications getting faster and more reliable, or should we also continue seeing whether we need to improve the procedures we do, or have the local systems running in a way to compensate with possible variations on the line?
I think it's a combination of both. I think you're absolutely right. I mean, one of the things that was actually, I showed the data just at the end, and what you see is there's a processing time for the image processing, which is actually quite long, and takes out, and that will just come down just simply as computers get faster, and so that will just improve as we go along. The control data we actually send, it's relatively low latency on the control, which is good, but you understand it's 20, 25 milliseconds. If we wanted true haptic control, like normally we talk with haptics of kilohertz, right? So we're not going to get that, at this moment in time, we're not getting that. So we do need to look to see if there's things that we can actually do. So in terms of making a stable contact, 25 millisecond latency is good, but it doesn't give us haptics the way people who work in haptics want to have that. So there is a need to do both, I think. Moving from 5G to 6G to in the future, these things almost certainly will improve. But I think what we have with 5G is the real possibility of doing something. With the old systems, the latency was too long, and therefore telesurgery was not a true possibility. I think with 5G, we can do this. And so the idea that 20 years ago, they did the Lindbergh operation and nothing really happened since then, I don't imagine that in 20 years' time, that will still be the case.
Oh, fantastic. And just a quick one. From your experience with what you have done already, reliability is there? I mean, you can trust the 5G network that you used, or are there still occasions where it drops out, and you need to be prepared for that, I suppose?
This was an experimental system. So this was actually in the early days, even of 5G. It's not, but even then it was really quite reliable. We were very surprised with what was going on. But that again goes back to what you were actually saying. If you have certain levels of autonomy within your local robots, then you can actually deal with that just in case. The biggest problems we actually ended up with were more operational problems, things like smoke. I probably doesn't show up, but the smoke that actually comes off, really, they couldn't actually see, because the area is so small and there was no ventilation, that the smoke was taking a long time to clear away. And that was an operational problem. And that actually delayed them more than the fact that the system would actually go down. It was a bizarre, it was actually a surgical problem that was more of an issue rather than the communication problem.
Thank you.
It does need to be improved. Things like as I said with the Phantom, with the Omni, when we moved the scaling, we made it really conservative. We were frightened they would crash everything, and so we made it. And they went, no, want bigger movements, faster movements.
Thanks a lot. Fascinating. Yeah, thanks a lot.
Davin, I have a question regarding the operating room setup and how the interface will be. Yeah. In one of the slides, we saw Leonardo operating with the, let's say, in-person console. Yeah. And then you showed the new system that then will be used in a 5G teleoperation. Yeah. So do we need to rethink then? How do we actually design our consoles?
The thing we give several options, because I think the thing you would find when you work with medics is that no two medics want the same thing. And so we had the option that they could use the microscope exactly as so they could use the tablet, but they could still operate with the microscope. They could use the tablet and they could use a virtual microscope. They could use the tablet and they could use an external screen. We give them all the different options and then said, choose what suits your style most. And so I think, yeah, there will be different operating rooms, but they'll almost be tailored to the surgeon, because we find that they often want different things. Some people, the tablets we use, some people wanted different tablets. Some people wanted tablets, so you like more like an iPad where you actually had an image on the screen. So the one you actually saw was blank. There was nothing physically to see, but other people actually wanted to see on the screen what they were also seeing. And you think, why? Because you're not looking, they're looking at the microscope, but it's like, oh yeah, I want to look away sometimes to actually, and you want, that didn't seem logical, but they still asked for that to happen. So we tried to produce a variety of options to customize. And then we said to different surgeons, try the different ones, tell us which one you like.
Okay, that's very interesting. Thank you very much, Darwin.
Welcome.
Very, very interesting work and inspiring work. A lot of new things will come out of that when you enable 5G teleoperation, I'm sure.
I hope so.
So thank you very much. We're going to our next speaker. Our next speaker is Cosimo from TU Delft, and he will be talking about learning and control of continuum soft robots.
So, hello. Thanks, Alga, for the kind introduction. Let me see if I can share my screen.
Yes, we can see your screen.
And now it should be in presenter mode.
And it is.
Okay, that's great. Thank you. So again, thank you very much for the kind introduction and for inviting me to this very cool workshop. I have to say that this presentation would be kind of on the other end of the spectrum with respect to the one that Darwin gave. So it will be about generic soft robot. I do not do research in surgery and stuff like that, because I don't have the stomach for that, unfortunately. But I hope that still this can give some nice take-home message for people attending. So, okay, we all know what a soft robot is. So it's a mechanical system or robotic system embedding in their mechanical structure, purposefully designed component elements. This is at least the definition that we gave in this survey paper that we recently wrote together with Manuel Catalano and Antonio Bicchi. So there is this spectrum, which is more inspired by vertebrate animals, but today I'm going to talk mostly about what is nowadays most commonly called just soft robots, so continuum soft robots, so mechanical system inspired by continuously deformable animals, so invertebrate animals like octopuses. And as we all probably know, there have been around for a few years some quite cool designs, and yeah, this is just six of them, but that there is very plenty of them around, and so it's should come as some surprise when we look at the tasks where soft robotics should be the most suitable, at least in principle, technology, like interaction or dealing with unknown environment. And we see that nowadays still rigid robots outperform soft robots in these tasks. This is actually the only exception is probably actually some application of surgery, I guess, but on all the others, this is still the condition in which we are. And I am probably quite biased here, but I would say that one main reason for this to happen is because we still have to deal with the completely, at least solve at a good level, the control problem. So the problem of developing a low-level brain for our soft robots, and this is a quite intricate problem that has been addressed by many scholars in the last few years, and I will just discuss today about a few of the takes that we are looking at. So, and when we look at these problems, we can identify, I think, three main components producing intelligence. One is the soft body itself, and the well-known concept of embodying intelligence that this has. And the other two are models and machine learning, at least in our works. So let me start with what we can what we can do by not using machine learning, but just relying on models. And so the overall structure is the very usual one. So we have our soft robot here, we have a set of actuators, a set of sensors, and we have a desired behavior that we want to implement on a soft robot, and we want to do that by means of a model-based controller that integrates sensors and produce actuations. And a way that has been that is very popular since several years is to approximate the robot in a quasi-static way, so to try to look at the problem on a kinematic point of view. And in this context has been popularized what is so-called piecewise constant curvature models. And the idea is to look at your soft robot, and you can often identify a sequence of segments, and these segments can be approximated typically with the arcs with constant curvature. And the reason being that in soft robots, it's often the case that torques are dominant with respect to forces, and if you have pure torques, these constant curvature segments are indeed an exact solution for your infinite dimensional PD. And then you have a kinematic model that is strongly simplified, and a configuration space that it's just the set of the local curvature for each of these segments. What we did was to borrow from this very well-known model and to add some description of the distribution of the inertias and the stiffness and the damping and whatever, and just to build a dynamic model up to that, which was of course nothing super innovative. But then I think what is nice is to recognize that this structure is very close to the structure that we are used to in classic robotics. And then we can start thinking now, an interesting part, to use these models to solve problems that we are maybe more used to solving classic robotics. And one of that is trajectory tracking configuration space, that in this context becomes trajectory tracking in curvature space. So you have a set of pattern of curvature at each of these segments that you want to follow, and you want to devise a controller that eventually bring your system to follow those patterns. And this is a block scheme of one of the controllers that we propose for that. It has a feed-forward component and a feedback component. And again, I will avoid details to not bore you. But what is interesting is that once you have at least a language to describe these systems, you can start proving things, and so have some reliability of what you are doing with respect to the performance, which is of course very important. But probably even more important is to see if it works really in the practice. So this is an example of trajectory tracking in closed loop. Hope that you can see the video nicely. So we have here a desired pattern of curvature in black dotted lines, and an actual evolution of the curvature in colored lines. And the controller ends up specifying this quite complex a pattern of torques that at each segment that in the end are generated by inflating and deflating these chambers. And yeah, these are other trajectories that we could end up follow. And I always like to point out about this trajectory that it's this seemingly easy task to keep these two segments straight while this top part oscillates. So I did not tell that, but this robot is, I mean, it's not super heavy, but still has quite non-negligible inertia. So it's a pretty long robot. And so keeping these two very soft segments straight while this one oscillates is quite hard, and it requires a pretty fine understanding of the coupling, the dynamic coupling between the two elements. And so once we had this you had this kind of framework in place, you can say, okay, let's start play with different things. Like, for example, let's see how we can reliably interact in the environment, because in the end, this is the main goal that for soft robot, I would assume. So you can do that with some Cartesian impedance controllers. And also we worked on the extension in the 3D world. It's pretty straightforward once you introduce the right models for working in 3D. And also applied these results to different kind of continuum or soft robots. This is just nice applications. Yeah, this is actually not submitted. This is recently accepted, but is like large scale soft locomotion, and each leg is moving according to a model-based controller here. So so far, models and soft robots works pretty well together, even if the model is very rough, and that's it's my claim, I guess, but we could. We are working on how to formalize that, but it's not this is material for another talk. That's these very rough models can be used in virtue of some embodied intelligence of the software robot itself that kind of take care of the extra degrees of freedom that we neglect. So, but apart from that, these two works already pretty well together. So why should we think of adding machine learning? Yeah, of course, there are several reasons, but one place where I think there is a lot to gain from adding some machine learning is in perception. So we have here our standard loop that we had before with our soft robot, in the real world, our controller. And if you really want to go in the real world, you cannot rely on like onboard on exoceptive sensing, like motion capture system and stuff like that. You have to be able to use some advanced sensors and some observer to inform your controller. But on the other hand, our controller requires a pretty good stream of information. So how can we get that? So we can look back at our soft robots. This time is a three-dimensional one. If we look at one segment, there are multiple ways in which you can think of sensorizing it, but I will not go in detail this, because this is the realm of Ryan Traby. So it's about. I will not attempt to go into detail in that, but I can show you a nice video. So the idea here is to have a scheme that you can obtain by laser cutting kirigami pattern from a very simple material that you can buy off the shelf. So you just need a laser cutter for that, and in the end you get a scheme that can work as a strain gauge basically. So I have a characteristic that of resistance that is proportional in some way to the deformation. So okay, so let's think about adding these sensors on the robot. So then what we do, and that's the big question, because in the end these sensors are pretty cool for several reasons. They're very robust and very cheap, but on the other hand, they have a super non-ideal behavior. It's very non-linear, a lot of hysteresis and variables that are difficult to model and to observe. So when you find yourself in this condition, often the answer that comes to your mind is, okay, let's try some machine learning. But still, this is not a simple solution to implement, because it's clear what you have as input, so the output of these strain sensors, but what about the output? So because the robot itself is infinite dimensional, right? So what you could put as output is some configuration of some point along the robot, but this would work, but would work just to predict the configuration of that point and not of the whole robot. So what you can do instead is to use models, and here kinematic models, and we use a particularly stable one that we propose, but is really a detail, to generate, in a sense, low dimensional description of the robot, so a kind of model-based latent space for our LSTM to learn into. And in the end, this model is parameterization for each point along the robot of the position and orientation based on just the 3 variables that are, so again, infinite dimensional, we learn, and we work in R4, and then we map back to infinite dimensional using a kinematic model. And the nice thing of this, the first nice thing of this approach is that you can then reproduce it for modularly for each segment. And the second nice thing is that here we are in the realm of classic kinematics, so we know how to combine these things in order to retrieve a full shape, a full description of the robot behavior. So, but still we have quite deep structure embedded here. So how can we get a good data set? And the way in which we did that was to take our soft robots, add some our skin, and put it into a motion capture system, and we did several hours of random inflations, and from the one hand we collect the raw potential differences at each sensor, and on the other side we extract this low dimensional latent description from the motion capture system that we use it as a ground truth. And then we train our network, and these are the results for very simple motions. These are in the validation set, they are not in the training set. And what you can see is in black the output of our algorithm, and in red the ground truth coming from the motion capture system. You can see that in the steady state behavior is actually quite good, while the transient, as we have some kind of low pass filtering behavior, but still it's pretty good. You can see here the evolution in time in the latent space. And here you have similar analysis for less more complex evolution that still is in the validation space, validation set. Okay, so at this point we started from these ideas. What we have is actually some kind of new sensor, some observer-ish, I would say, so with some machine learning, and we have able to extract the state. We still have to due to COVID, as usual, we still have to meet again and test the whole closed loop. But what we could do was to play with something else. So say, is this all the information that we can extract from this data? And the answer ends up to be actually no. And there is another important thing that you want your robot to have, which we can extract, which is tactile capabilities. And I will go very fast with that because, as usual, I have much more slides that I should have included. So the idea is to have some kind of algorithm that looks, so is the input of the algorithm, looks at the configuration of the robot and to the inputs, so the pressure in this case, and understand which are the interaction forces. And we use machine learning to complete the kind of a model-based solutions. Again, I will not go into details, but we can discuss them later if you are interested. What I want to stress here, I think it's important, is that the only thing that you need here is your pressures from the pressure regulator, and we have them. And the other thing is the output of the previous network, which is this latent space description. And then the algorithm will use some kind of internal model, which is mixed learned and known a priori, and then integrate it with the measurements to estimate if there are some external forces. And again, the nice thing of having at least some kind of model laying beyond our theories, that we can prove things, and we can give at least in average, and in terms of average, in terms of variance, some bounds in terms of the quality that we can expect from this machine learning based solution is one nice thing. And another nice thing is that having a model already allows you to do training only on free motions, so you don't need any examples on actual interaction with the environment. So there's some examples of free motion, and we could actually use also the data set that we collected for the previous paper. And then when it comes to the validation, then we can start interacting with the robot and see here. I mean, you can see with a stick, and on different segments from different sides. So first from left and then from right. The output that we get from our LSTM is something like this. So this is going to serve as input from this other algorithm, and this is the output of the algorithm, in which you can clearly identify when the contact is. Of course, there is some cross-talking and some dynamics, but I think it's pretty clear when the contact event happens. And this is still in a description which is not super easy to see, but if you then transfer it back in Cartesian coordinate, you can clearly see that this is just the plotting of this thing in the Cartesian coordinate. You can see that clearly identify the pushing that is produced by the stick in the correct direction. And you can also do, like other things, interact with the environment and detect if you have contacts or not. Again, pretty clear. So I have 5 minutes left. I guess that let me see what I can jump to. Okay, I will be very quick. So this was a lot about sensing. There is a lot that we can do about control as well, and but in order to understand what we can do, we looked back at the natural examples, and in particular to some works about how humans learn to do motions, and especially manipulations when we have big unknowns in the dynamics. So we are all familiar with the situation in which you have like some can of milk, and you expect that the can is full, and then you lift it and that you discover that it's empty, and you have this overshooting. But then what happens is after when you do that again, you are again perfect in using this in moving this object around. And so we actually Marco and Kyushi did these experiments in which they tried to formalize this thing by asking subjects to lift objects with that unexpected mass distribution, and in a way asking to keep it vertical, and in a way with a setup that was in which we could measure everything, so both the kinematic information and the force information. So this is the object, and the unknown mass distribution happens here. And what we wanted to do was to try to model what happened, to maybe transfer it to some robotic applications. And so the idea, you have here some object that can roll. The subject is looking at it, so you can imagine some kind of signal from the subject. And the trick here to get to a nice modeling of this behavior is to first start by identifying the events in which this learning happens, and then create kind of two-dimensional time domain, which you have the standard time here, then you have the iteration domain here. So in each iteration you have a different attempt, and this is actually what's in control theory is called iterative learning control. And so we could leverage again on this formalism to describe this behavior. And in a nutshell, the cool thing is that you can then close the loop in iteration. So you can learn tasks by integrating control action and error from previous iterations at any time. And this, we proposed an algorithm based on this idea, which turned out to explain incredibly well the data from humans. So it's a very, very simple algorithm in the end. But what it's more important is that we could then more recently, after a few years, come up with a proof that this is actually works for generic systems, this kind of algorithm that we proposed. And what is even more important is that you can then test it with real systems. So this is a Delta robot, which is an articulated soft robot. So you have elasticity at the joints, softness at the joints, but the robot is still rigid in a sense. What you want to do is to learn how to track the trajectory that the user specified, and this can be done in this way with this process of learning by repetition that as humans we are so familiar with. And in the end, so this is a learning process that it's based on the model in the sense that we use the knowledge of the model to understand how to update the control action, but apart from that, there is no model-based part. And in the end, the system is able to learn to track the desired trajectory in a pretty accurate way. You may say, okay, this is easy because it's not a continuum soft robots, and this is true. I mean, it's at least it's easier. We don't have yet experimental validation of that, but you have some simulations of a pretty complex problem, I believe, which is to stabilize the vertical configuration of an inverted soft pendulum, and it works quite well. So in a few trials, the robot learns to go from down to up. You can imagine this kind of robot with a single torque applied to the tip, as for example having two tendons. Okay, I am beyond my time, so I have to skip all the nice things that I wanted to show, and I will run directly to the conclusions. So I think that I hope that this talk may have give two take-home message. One is that soft robotics are ideal playground where to experiment with combining model-based and data-driven strategies. And in my opinion, there are deep theoretical reasons why this is the case that I did not have the time to discuss here, but at least I think it's an experimental evidence that this is the case at least. And then that models can indeed help machine learning in this context to become faster, efficient, and safer. Okay, thank you for your attention.
Thank you very much, Cosimo. It's very much a thorough understanding of the kinematics of soft robotics or soft robotic structures, which I very much enjoyed. I invite everyone to ask questions and would like to start with a question regarding the how should we drive the kinematic models in future. So for example, if we look into concentric tubes, they're made out of one material. It's, let's say, simpler to model the physics-based model for these type of robots. If we look into more complex soft robotics, there is different materials integrated into different type of composite materials. Where do you think do we need to push the complexity of these models, or do you say, okay, we can in fact more focus on the control strategies? If we have a good control strategy, the kinematic model is can be basic.
No, I definitely think that we should push more towards the models. It's in a sense, it's not my job, but it's in Federico's job, for example. So I think we will know more about the more advanced model in the talk by Federico or Randa later. But yeah, so I'm more a user of these models. But if I can comment it further, I think that still in software robotics there is a distinction between models that you use for control or planning or intelligence, whatever, and models that you use for simulations. And I think that for control it's important to use simple models, while for simulation you want to be as accurate as possible and to validate your model. On the other hand, I think it's important to have some kind of middle ground, because you have to. I'm very keen of proofs, mathematical proofs, because they give you this, at least in a certain extent, the certainty that things will work. And I think it's important to understand why and in which conditions these simple models are working, because then we can know what to do when they fail, and how to recover from the failing.
Okay, thank you very much. Before we come to Caspar, I just want to go to Karthik, who asked if the position control of soft robotics will reach the accuracy of rigid robots at one point. I guess that's maybe for open and closed loop control, but Caspar, please.
Maybe I can just combine my question with that one. I saw that question from Karthik there. So first of all, thanks to Cosimo for the fantastic presentation, and I totally agree with the idea of using models and then to build on those and have machine learning techniques, etc. In addition to cope with the non-linearities of these systems. Anyway, so the question is about whether position control of soft robotics will reach the accuracy of rigid robots. My question I have is, do we need that? Do we actually need this kind of position control? And I want to link it also to the example you gave about the walking robot. Do we really need a sophisticated controller there?
Thanks for this question. So I think that we need a sophisticated controller, but not an over sophisticated controller. But I think that often, I think in science in general, but for sure in control theory at least, which is the area that I understand a bit better, there is this thing that it's relatively easy to get to easy results, and then you have to get very complex. And when you really understand things, you can build a simple algorithm again, but with a deep understanding of what is going on. So I think that right now, at least me and my group, we are in the complex area of the spectrum. But I think that as a long-term, medium-long-term goal, definitely we should end up with simple rules. And already something can come out that's to show that that's about these simple rules. But in terms of goals, in terms of precision, I don't think we should aim to be as precise as rigid robots, because otherwise you can use a rigid robot. I don't think that soft robots are better than rigid robots. I think they are better in some application and worse in the other. If your goal is to get as high precision as possible, then you should use a rigid robot. That said, I think it's also important to have a reasonably good precision when it comes to move the tip of the robot, for example, or something like that, because in the end, if you want to do some operation like entering a narrow space, and you have at least to be able, even in complex condition when you have dynamics involved and stuff like that, to do that operation more or less.
Thank you.
Thank you very much. There's one from Scotland, from Luigi. Hello, Luigi. So your question is about the pressure regulator that are used to control the soft robot. And the question is about the instability and delay. Have you included any model of a pressure controller in your control loop?
And currently, the answer is no, or at least only in very simple ways, like in the usual, like a low pass filter and input to your model. But we are working on it. So I hope that I will have a paper to submit to the next RoboSoft about this topic. Also to come to Edinburgh. So
fantastic. New collaboration there happening right away. I suggest to have a 2-minute break. We usually have a 5-minute break, but we were a little bit late. So 2-minute break, and we will see us again, each other again at 3:18. And we have more interesting talks from Robert and Federico, in fact. So see you in a short while.
Is it okay if I share my screen, Helge? Just to test.
Yes.
Excellent. Thank you.
Of course.
Okay.
Yeah, we can see your slide, Robert.
Perfect.
Fantastic. And I think we can continue. 2 minutes is shorter in virtually than in person, I guess. But here we go. We have Robert next from ETH Zurich. And I'm very excited to hear more about model-based control of soft robots tackling manipulation and locomotion challenges. The floor is yours.
Thank you, Helge, and thank you for inviting me to this format. I'm very happy to speak to you today and get a bit more into what my past research and passion has been on. And I have to give a heads up, I will have no explicit medical applications. I appreciate the medical field. I've worked as a systems engineer at Auris Health before I did my PhD, but that was already in 2012, so that has been a few years ago. Since then, they have gotten acquired and gone through some turbulent times, but I've been focusing more on soft robots, and today I will be talking to you about how can you quickly, how can you build them, but also how can you control them and what can you do with them? And hopefully that will be an inspiration to people building medical systems if some of these technologies can translate or can be applicable. So let's see. Well, so how I usually like to motivate the work in soft robotics is I like to look at the question of nature has primarily soft-bodied structures. I mean, there's things like skeleton and bones and rigid parts, but there's a lot of softness to it. And they can do great things like here, you see a fish swimming upstream. Some of you might have seen this before. What's particularly interesting about this fish is actually not alive. It's dead, but it's still capable of swimming upstream. So it's just due to its body structure interacting with the water, and it can leverage a particular flow phenomena to go against the stream. And similarly, we see things like an octopus underwater is capable of doing multiple functions with its completely soft structure. It can swim, it can enter confined environments, and it can also wrap around its prey and do all of this with one single body. And even above water, we would see an elephant, which has been inspiration to the research, both Cosimo's and mine in the past, where we look at, they have an elephant trunk that can do a lot of tactile interactions. And so the question is, how can we reproduce this in robotics or reproduce this to make functional applications that could even be useful to medical applications. So the questions I've been following down is, how can you build flexible, adaptive, and very efficient systems and how to reproduce this dexterity and safety in real robots? So just to give you an overview, this is kind of my outline, what I will be speaking about. And it is basically, how do you make soft robots and how do you go about doing this? I will very briefly touch on this because most of this has been more older work. Then how do you build integrated systems out of these soft robots and what are the challenges? How do you model multiple of these soft actors, integrate into a more complex system? And how can you do control and learning on these systems? So starting off with making these robots, I just want to give you an idea that all the robots I will be touching on today can be categorized into these 4 different types of fluidic actuated robots. So you either use air or you use hydraulics to actuate them. And you can then build either something called a cylindrical design, you can build a pleated design, a rib design, or a fiber reinforced design. And they all have their gives and takes of what they can do well and what they cannot do well. And I've tried them out in all these different applications. You can see at the bottom. So like we have a fishtail, we have sort of elements that we use for grippers or for planar arms, or even how we build 3D arms using these different morphologies. And so you can fabricate them using casting principles. So either by multiple steps of making them, or you can use lost wax casting. You can print them, or you could even print them with integrated functionality. And if you look at the way you actuate them, you might wonder, well, how you bring actually the pressurization into these hollow structures. Well, you could use something like a displacement pump. You could be using cylinders, pneumatic cylinders. You could be using valve arrays. And that's sort of kind of like are the major categories I've seen for actuation of these soft fluidic actuators. So with this, I want to directly go into, just to give you this background. Now I hope you understand a little bit how are these systems running and how they're actuated. Now I want to go into what systems can you make out of this. So one example would be the soft robot that we've built, which is an underwater robot that can explore the underwater life and kind of spy on real underwater life and mimic it to some extent. And this is just using a single soft actuator with 2 chambers. And it allows us to actually deploy this in the ocean. It's fully integrated, there's no tether to it. And we just showed that we can actually build a soft robot and deploy it in the wild. And so with this, we were able to go into multiple depths, and we could actually look at various other species and observe them and see them both with our onboard camera, as well as the diver's view several meters behind. The diver itself is using a remote control module. I'm not going into this today, but it's able to look at these different species. And so this was a challenge to build a system, to integrate, to put everything on board and make this one structure that has a pump and has these actuators. So then another integrated system with a single actuator was this work where we took a pleated gripper design using soft actuators and making, for example, a design that can pick up objects and use this built-in strain sensing to do proprioception. And that was allowing us to identify what different objects we were picking up. It was sort of an initial step towards this direction. We were still not at the point that we could say we can actually identify it in various grasps, because we had to control the grasp that we were interacting with in order to have a reproducible object identification with such a gripper. But then if we did that, we could actually say we can identify various objects that we're picking and just learning a representation. And there were no cameras involved. We could just then rerun this experiment using just the built-in strain sensors. With other work that I've done together with my former lab mate Ryan Truby, was to then build, for example, a gripper that had these sensors directly printed into them, and to achieve even more resolution on these grippers. So we would not just have one of these sensors built in, but we would have multiple of these built in, and we could do things like you can see here, picking up a cup, for example. So now I want to go to a more recent integrated system that I've built at ETH, like my team has built at ETH. And so this is called Roboa, which is a steerable vine robot, where we took a previously shown principle of eversion and vine robotics and applied it to a system that can actually deploy in debris and can be used to find someone who is trapped inside of a collapsed building, for example. And so just to give you an idea of how this works, here you see the vine robot principle. This was the initial prototype that the team built and tried out with a nylon ripstop tubing that was trying to understand how the principle actually works. The team in Stanford had originally deployed or developed such a system, but they wanted to advance it and figure out how can you actually steer this inside of, let's say, an occluded building. And so they then went ahead and said, okay, let's build a complete system that has included into this a robotic arm that we can then deploy in the wild and steer it remotely by just seeing the camera feed and other sensor inputs that are mounted into the head, and actually see how, for example, a rescue troop at a military site can use this to see, for example, someone being buried in debris. And just to give you an idea of what was involved in this integrated system, so here you see it was primarily figuring out, first of all, what tubing is reliable and can be used. So it was, in this case, using a ripstop nylon with a TPU coating, and we're talking about a structure that has a diameter of about 100 millimeters, and the first robotic prototype was 17 meters long. And then we took it to add this internal robot that is 3D printed, and it has the built-in pneumatic valves all integrated into the arm, so it is untethered from its base and it can just go into the structure. And then you would use this, for example, to look at to find a person that's buried, then be able to speak to it. There was a speaker built in, there is a microphone built in, as well as IMU and camera to actually communicate with the person buried. We had wireless communication to this head. And finally, this is the complete system, how it looks like. It has a supply box that can be just carried on site by someone who is trying to rescue a person in a building. So just to show you some of the things that we were able to do, this is a testing site from the Swiss military, and we deployed it in there and tried it out. And it was capable of doing various experiments, and we were able to show it was working for this principle. And we are working on a second generation at the moment that has several of the shortcomings fixed, but we'll see in a few weeks how it's going. So this is basically making a vine robot steerable was one of the contributions, putting all the pressure distribution on board, deploying it in a debris field, and then in the end also, showing that it actually works with real people. And now I want to jump from going from integrated systems to talking about how could you actually model these so you can have them be more autonomous, don't requiring a remote control or any of these aspects. All of the systems I just showed you required some sort of remote control, and eventually we don't want that anymore because we want the systems to be intelligent and autonomous. So I will be talking about 3 different areas of investigation that I'm looking at with my group. One of them is how can you use fast nonlinear finite element methods to model and optimize soft robots. The second area is how can you use reduced order finite element methods to control these soft robots and have something that can run in real time. And I will also be quickly speaking about minimal parameter models. Cosimo just now already mentioned this work that we did together, and I will not spend too much time on that. And with this, first I want to speak about our work that we recently published at SIGGRAPH. It is essentially a robotic system that is capable of taking both the design space and the controller space that you define by having various instantiations of a design that you believe could be great, and you have the ability to freely interpolate between these designs. Plus, you have the ability to take a controller design that allows you to also optimize the controller at the same time as the geometric design. And we do this by having a differentiable simulation, which is here in the center. You see it as the third box in this screen. And we then eventually have the ability to optimize for a loss function, to minimize the loss function for particular tasks such as fast swimming, etc. So what we did here essentially was to say, we take, for example, these 3 different swimmer designs, and we are then able to take them, interpolate with them, having all these muscles built into the structures, have all these like continuous integration, continuous variation points between those designs. And then we are able to say, let's take this and optimize it for a control policy and a design at the same time. And to show, when you start off with just the 3 initial designs, you can optimize for the control only, or you can optimize both for the design and control. So we came up, for example, with this hybrid sim you see here at the bottom, that is faster. It has its own optimized controller compared to all of the initial designs. So we were not able to come up with this design initially. It came out of this optimization process. And with this, I want to jump forward and show you we were able to do shape optimization of various types. So for example, here we start with this swimmer design, and we then eventually find this shark design that interests us. And you can do this for multiple objectives. So we can say, hey, let's look at, we want to have a Pareto front that is a trade-off space, the trade-offs between, let's say, a high-speed swimmer on the top left, a medium-speed swimmer here on the center here, or we have a high-efficiency swimmer that doesn't use as much energy. And so you can design for these multiple objectives using this approach, and it goes fairly quick. And we believe that this is an approach that will allow us to do a lot of interesting future designs that can solve various problems, because we can encode these tasks in this framework and we can very quickly solve for it because of the differentiable nature. So with this, I want to say other approaches that we've looked into is how can you use finite element methods, but you actually use a reduced order model. And I have only one slide on this, and I want to just quickly give you an idea. So you can obviously take a dynamic FEM model that is highly dimensional, linearize it around the equilibrium points, and then use a method, for example, proper orthogonal decomposition, but other methods are possible. And you combine it with a state observer, and then you can actually do linear state feedback control on the structure to do control of, for example, our soft robotic arm. And it allows you to use this model in the loop to do real-time control. And I wish I would have had more time to try it out, but I'm currently in the process of doing this and seeing more results in this direction. So now going to these more minimal parameter models, the third thing I was showing you on the previous slide is how can you take, for example, a constant curvature assumption, Cosimo was briefly showing this, applying it even up to a 3-dimensional arm and mapping it to a rigid robot model that allows you to say, hey, this is an approximation to a model that allows us to very quickly and rapidly calculate the dynamics of the system. So while on the left side, we would assume our arm to have constant curvature bending, on the right side, you see we have substituted this with a rigid model that approximates this deformation. And that trick allows us to then take the rigid robot model, calculate the dynamics for it, and then map them back into this piecewise constant curvature space that allows us to say, okay, our constant curvatures can be dynamically modeled using this approach. So you see we can account for inertial effects, choreal centrifugal gravity, and even for external forces. Down there, I'm just, for the interested audience, saying this is essentially what you have to do. You calculate the dynamics in the augmented space, and you then just map them back into the constant curvature space. All right, so this being said, we can then, for example, go ahead and apply this to our systems. For example, the soft robotic arm. We take this minimal parameter model. We then have either a curvature tracking approach. We have that approach to then track the robot arm and move it around in space and trying to get minimal tracking error for this arm. We can do the same also in the Cartesian and effector space. So we've shown this so far on the 2-dimensional arm. And yeah, it so far worked fairly well on this. I'm not going to show much of the results to this work, but here you can just see it in action on the left. So this is, for example, following an element where we are keeping the bottom 2 segments stiff and the top 4 segments are actuated. Cosimo earlier showed our S-shaped arm. This was another example where we used it as a 4 segment that is being controlled while the rest is being, quote unquote, being kept stiff, even though the whole soft arm you see on the left is actually completely soft. And then we also were using it to track the environments and to do compliant tracking, or we were using it to do 3D tracking. But all of this, to be pointed out, was using motion capture markers. So now going from here to a system where you see we can actually also do this proprioceptively. So we build in the right sensing equipment to then have the ability to move this arm around, have a gripper on it, and to do actuation with this. And we can reconstruct the state with this setup, and we can show that we do all of this to an extent without using the motion capture. We're just using it as a benchmark. So here's the approach that we chose. We put in a flex sensor into the structure, and we also dived a bit more deeply into how can we model our specific fiber reinforced design in this case. So combining both a flex sensor in the center of the arm plus understanding how the fiber reinforced design works, we were able to say, okay, let's make a proprioceptive arm that, for example, can even sense what it is picking up, as long as we make the assumption that we know where the force is exerted on the soft arm. So it can, for example, tell you how much are you holding there, how heavy are these grapes. And so here's an example of how we can reconstruct the state, and it's not using any motion capture markers anymore, all by using these built-in flex sensors. And similarly, we used it for the force estimation task that you see here. So we can say, okay, the arm is capable of re-estimating how much force is applying to this arm at a particular point in time. So now I want to jump to the last part, and I should have looked at the time, but I think I'm pretty close to the end. We also looked at another way of modeling these states. Instead of using these more model-based control approaches, we now want to use a compositional operator instead. So recently people have looked at Koppeln operators, and what we want to actually do is we want to understand how can we encode the state of a robotic arm or of a cheetah robot or any other robotic system, but also reason about its uncertainty at the same time. And so what we came up with is to say, well, we encode the state that we take from a robotic arm, for example, its augmented state for the soft arm that's here shown in the visualization, or for this half cheetah example that's very commonly used in the reinforcement learning community. And we encode it into a probability distribution, which is just described by its mean and by its variance. And we learn these networks to describe this distribution. Then we take those inputs, we build in our Koppeln operator space that recursively propagates the state forward in time. And then we observe the output of this to say, hey, this is basically what we are looking at, mapping it back from this lifted Koppeln space, which is a linear space, back into the nonlinear space of the state that we're observing. So that's the theory that we kind of advanced from previously non-stochastic approaches. And we then said, okay, how do we train this whole system? We take our states and we essentially move them forward. This is our forward reconstruction error that basically takes the output on the right side, and it looks at how well is our state reconstructed within our state variable, our Koppeln state variable here. And we do this all under the constraint of having a linear forward propagation with the Koppeln operator space, which is these matrices A and B. And at the same time, we also say we need to initially encode these observables. And so we do this with this formulation, whereas our encoding is doing this sampling out of a zero normal distribution. And we just take out our state variable in the Koppeln space out of that. And with this, we combine it with a model predictive controller that would allow us then to do state feedback control with a forward-looking cost optimization that's described with these formulas. I'm not going to dive into more detail, but you can basically then use this to, for example, do a closed loop feedback control on the cheetah robot. This half cheetah robot is shown here on the left. And so we tried and validated this first on some canonical control examples. So this is a card pole example where we were able to use this controller to control it. We were also able to run this higher dimensional half cheetah, like two-legged example. And we were also able to apply it to our soft robotic arm. Here's just a visualization, but it's basically the augmented arm that I was showing you earlier. And similarly, we then showed the actual stability of the system. So with this approach, we were able to deal with way higher disturbances applied compared to like a state actor critic model that is a fairly state-of-the-art reinforcement learning approach. So in the card pole, you see, just going back again here on the left side, let me stop the video on the right side. So you see the card pole, we keep putting in about 6 times the control effort that you would typically be exerting on the system. And the robot is able to sustain it because of the way that we are accounting for the stochasticity of the system. So we have noise in both observation as well in control noise, or like system noise that we are able to compensate for. So we compared this to previous Koppeln operator approaches and also to state actor critics. And we were out like performing those comparable benchmarks. With this, I want to first acknowledge my previous co-authors while I was at MIT and doing my PhD. And I'm just focusing on the people that were involved in the works I've shown today. And I'm very grateful for the time over there, because without all of the people, including my advisor, my committee, and all of the folks that helped on the different projects, also including Cosimo, I'm very grateful for this time. And it's kind of like shaped directions that I'm now taking with the lab to obviously a very large extent. And my current set of collaborators, I want to acknowledge them, and like I'm very enjoying to work with them in various fields. So that goes all the way from biohybrids to actuators to modeling, and also aerial and learning work, both within the Swiss realm, but also beyond. And I'm very curious to see if people are interested to do more medical applications in the future. And obviously, I want to say thank you to my group, which I had to start off during a COVID time, which was not an easy time to start a group and to establish lab research that requires hands-on work on robots. But yeah, a big shout out on everyone in the team. And just for fun of showing how much fun it is to work on soft robots, they sometimes think that what you're doing with them is actual real trash. And because they don't really want to do what you want to do, they just throw away your object and they say, hey, this is actually something to stump in and get rid of. And with this is my summary slide. Thanks a lot for your attention. And now I'm happy to answer any questions.
Thank you very much, Robert. Fascinating what you have been doing at ETH and prior to ETH at MIT. You said there might be not many medical applications, but I'm sure that many of these things that you have presented can be transferred also to soft medical devices and robotics. And it's actually very nice to see that they also work on different scales. I like to invite everyone to post their questions, of course, or just raise their hands. And let me just start with asking the question about the vine robot. So that's a very impressive work that you have been doing there, from getting the first prototype to deploying that prototype. When you model a vine robot, there's of course bending behavior. What I also noticed when we work with inflatable structures that are not really made out of a physical body, silicon body, but it's air pressure or hydraulic pressure that is actually inflating the skin kind of into a structure, that there's not only bending happening, but a lot of buckling.
Mm-hmm.
Have you been looking into incorporating buckling into your models?
Well, I've been looking into this because it becomes particularly problematic when you're trying to model fishtails. So in the fishtail structure, we have multiple ribbed segments. And after a certain amount of actuation and vacuuming on the other side of the tail, so if you have just two actuators on two sides and you start actuating, you get buckling effects on the non-actuated side. And so, yeah, I have been looking into this, and it's actually a very challenging problem to do that nicely in an FEM environment, because, yeah, you're basically going under contact and you need to account for this, something that you typically don't expect contact to occur. So it's more of a computational efficiency question of how do you solve this. And I don't have a good solution for it yet, but I have to work on it, because some of the, for example, fish robots that using these chambers, they require buckling to actually work.
Thank you very much. Caspar has a question.
Yeah, hi Robert, how are you?
Hello, Caspar.
Good to see you, and good to see your presentation. Really a fantastic overview there, and impressive work happening. I mean, you're saying that you're not the medical expert necessarily, especially for the more recent work you have done. But yeah, Helge said it already. You're working at different scales, and that is also very exciting. So I'm wondering whether you have maybe developed a feel for issues across scales. And I'm asking that question because if we think about minimally invasive surgery, for example, miniaturization is really key. Mm-hmm. So what's your view there? Is it easy to use the principles that you have developed and apply them also to much smaller systems?
I don't think it's easy. I think it really depends on all the boundary conditions to a system. If you have the luxury of your system being sort of stationary, so you can start off from a fixed route, then I do think it is doable. So you can take the Vine robot example. You can scale things down, and it would actually be an interesting thing to do going forwards, to take the same principle, but going down to, let's say, a diameter size that actually interests us from a medical application. So instead of 17 meters and 100 millimeters diameter, we go down to just a few millimeters diameter. And I think this is a challenge to embark on. We kind of like would say, we know how to do it in the large scale. Let's go about and do it in the small scale. And in the process of this, we will obviously encounter a lot of problems that have to do with when you miniaturize, those equipments don't exist anymore off the shelf. So you have to do them all yourself. So like what we can do, for example, here, buying existing valves, and we can put them into our like islands in between, not a problem. But doing it in a millimeter scale, a huge problem. So I think the engineering challenges are on how can you supply selective pressurization in these chambers to do, for example, a Vine robot that would go into a human body, just as one of the problems to point out. Some of these problems have been solved. For example, small cameras exist and that has been developed, so you could leverage this. But for example, putting pressurization into the structure itself instead of running through it is a big challenge for a Vine robot, for example.
Yep. Okay. Yep. Thanks a lot. Thank you.
Thank you for the question.
Thank you very much. And thank you, Robert, for presenting. Very nice work indeed. And I'm sure that there will be a lot of work that we will see that will be then applied into the medical field.
All right. Looking forward to it. Yeah. Thank you, Helge. Thank you, Casper. Thank you for having me.
So we are moving on to Federico, and I apologize that I have not seen your question in the chat, but Cosimo nicely answered your question in the chat, so thanks for that. Federico is at Khalifa University, has done a lot of work in modeling soft robots, and today he will present a geometric variable strain approach for soft robots modeling.
Thank you. I just share my screen. Can you see it?
We can see your screen, and now
Great.
also in full screen. Thank you.
All right. Thank you very much for the invitation. I'm very happy to be here tonight, actually, here with this impressive lineup of speakers. So thank you for inviting me. And so as Cosimo predicted a little bit, my presentation will be very equation heavy, unfortunately, so not as exciting probably as the one we have seen so far, but I hope I will be able to convey at least few basic concepts that I think can be useful to approach the problem of modeling soft robot. So my presentation is titled Geometric Variable Strain Approach for Soft Robot Modeling. So we are all very much familiar with rigid body modeling that are parameterized using joint coordinate, and this produces a minimal set of ordinary differential equations in the Lagrange matrix form that we all like and enjoy. It also enjoys collocation of sensor actuators and degrees of freedom, which is also a very important property, which make it suitable for design, analysis, and control, other than simulation. So the aim of the geometric variable strain approach is to generalize this method to the case of hybrid soft rigid system. So how we do that? The main idea is to see the soft link that compose the system not as a link, instead as a distributed joint, and then parameterize this distributed joint with a finite set of strain modes, which become the counterpart of the joint coordinate. By doing that and cranking the machinery of mechanics, we can inherit all the good property that we like of rigid robots. So in this talk, I will start with some theoretical framework, then I will move on with computational method we use to solve the system. Then I will show some numerical test and example. And finally, I will, maybe if I have time, I will propose an extension to nested row systems that are more in line maybe with the medical application. Here you can see some reference if you are interested in what I am presenting today. Okay, let's consider a floating soft rigid system as the one shown in this picture. And the configuration of a link of a link I with respect to its predecessor in this chain is defined by a curve g of x in the special Euclidean group or the group of rigid body transformation. As we all know, this transformation can be represented nicely by homogeneous matrix. Now, the first observation I would like to make is that this continuous curve parameterized by the curvilinear abscissa from 0 to L, where L is the length of the link, it is a definition that can be applied to not only soft link, but also rigid link. How? So for a soft link, this curvilinear abscissa identify the rigid cross-section that compose the link. While for a rigid link, we can imagine that this curvilinear abscissa goes from 0 to 1, and so we can build a virtual rod of length 1, where the x equal to 0 indicate the reference configuration of the link with respect to the predecessor, where x equal to 1 indicate the link at the end of the joint motion. Now, of course, all of these intermediate body are virtual. They don't have mass, they don't participate in the energy, but from a kinematic and geometric point of view, is useful to do this analogy, because now I can apply this continuous definition, and the work you do to the soft link, it's directly, with some simplification, is directly applicable to the rigid link as well. So first, now we take the partial time derivative of the configuration to define the relative, let me put this down, otherwise, okay. So to define the relative velocity, which is composed by the relative angular velocity and the relative linear velocity. This is well known by everyone. If you take then the partial derivative with respect to space, which is our x, you can define the strain of the soft link, which is composed by, again, angular strain and a linear strain. Now, this equation here is a matrix differential equation that can be formally integrated in space, and we're using the exponential map in SC3 that has this nice analytic formulation. Now, for the case of a rigid link, the strain is nothing else than the joint screw. And this joint screw is constant along this virtual rod that goes from 0 to 1. And so we can directly take the exponential of this constant joint screw in order to obtain the configuration of the link. While in the general soft link case, the strain is not constant in x, and so we need to employ what is called the Magnus expansion in order to find the configuration. This Magnus expansion, I will show you later how to compute it, but in any case, it is a series that involve the strain and the integral of the strain. Okay, moving on to differential kinematic. We seek now a relation between the time derivative of the strain and the link velocity and acceleration. So how to do it? So first of all, we equate the mixed partial derivative of the configuration G. This produces what is called a transpositional relation. That is very fundamental in this scheme because it relates the space derivative of the velocity and acceleration with the time derivative of the strain. Now, once again, and here we are also introducing some SE3 operation that are reported for completeness. Now, again, this transpositional relation can be analytically integrated in space again, and we obtain this very important formula that relate, once again, velocity and acceleration of the link, relative velocity and acceleration of the link, with the time derivative and second time derivative of the strain. Now, this general formula, this general kinematics, differential kinematics, is applicable to the soft link, but also to multidimensional rigid links. For instance, a spherical joint. In the case of a rigid link, I just observed before that the strain is constant, so this can be pulled out of this integral. And there are also other consequences that I will show you later. But it's important also to observe that in the standard case of one-dimensional rigid link, which is the one we are used to deal with in rigid robotics, all of this transpositional relation is exact. So all of this term that goes to 0. And then the integration becomes trivial, and we recover the usual relation between the joint twist and the relative velocity, as you can find in the best book of robotics. So this is nice because I think it connects the general story together. Now, coming back to the soft link, we need now to discretize the strain field. And we do that by employing a finite basis of strain mode, represented by this matrix, BC. And so we can now write our strain with this in this way, where C star represents the strain in the reference, the unloaded configuration. So I see, you can hear me, right? Yes, because I see, I hope everything is fine. Okay, so now inserting this strain, this discretization into the general differential kinematics we obtained before, allow us to obtain the geometric Jacobian and its time and the time derivative of the geometric Jacobian for any body and any cross section of the system. Okay, now that the kinematics is on the back, we can move to dynamics, and we start with the free dynamics of rigid and soft link. So for a rigid link, we can use the well-known Newton-Euler equation, where these Fj are the force and torque transmitted through the joint from one body to the other. For what concerns the soft link, we can use the Kosserath dynamics, which indeed consider the cross-section of the link as rigid, exactly as we have done in our kinematic approach. So here you can see the PDE that govern, the partial differential equation that govern the momentum equilibrium of a Kosserath rod. And those are the boundary conditions where, again, the force through the joint that connect the different body of the system appear at both ends. It's also easy to include the elasticity model, of course, in this model. The elasticity is an internal force. Here you can see a linear elastic model, but this formulation allows for any nonlinear model, which is very useful, actually, I think, because this will allow you to simulate also complex and composite material later on. It's also very easy to model trade-like actuation, such as internal cable. Again, in this case, those can be included as internal forces with a special constitutive law, we can say, which depends only on the distance of the rod, sorry, of the distance of the actuator to the midline. Okay, now that we have a differential kinematics and a free dynamics, we can combine the two things through the D'Alembert principle and project the free dynamics into the generalized coordinate of your system that are composed, I remind you, by the rigid joint screw and by the strain mode of the soft link. So you can project using virtual displacement of the link that has to be compatible with your kinematic. So by doing that, you obtain the standard Lagrangian dynamics in the standard form, where M is the mass matrix, C the Coriolis matrix, stiffness matrix, then you have actuation matrix and external generalized force vector. It's also interesting to know that this formulation is valid also for rigid link. You just need to remove the integrals and replace the distributed quantity with their concentrated counterpart. So now the remaining job that we have to face is how to compute those integral substantially, and all of those matrices, how we can compute them. And the Magnus experiment, many things we left over, so how to compute them. So let's see our computational method. So first of all, I want to show you the constant strain case because it's interesting for the rigid link, but also because it allows me to introduce quantities and equations that will be useful also for the general variable strain case. So once you assume constant strain, then the Magnus expansion that constitute your kinematics can be assume a simple analytic form, which substantially the Magnus expansion gives you exactly the strain, which is something that we have already exploited for the configuration of the rigid link. Now, as I told you before, these have several consequences into the differential kinematics. One of them is that you can pull out, of course, the strain from the integral. And the second one, and most important, is that it makes appear this integral that is called tangent operator of the exponential map in SC3. And this, since many people have studied SC3 a lot, you can find the analytic formulation of this exponential map in some books. Similarly, you can apply the same story for the relative acceleration, and this involves the time derivative of the exponential map, which is another nice analytic formula. So finally, for the constant strain case, which means everything is constant strain, so the rigid link are always constant strain. The soft link are assumed constant strain in this case. Then in this condition, you have for analytic formulation that allows you to compute the configuration, the Jacobian, its time derivative, and in return, you can also compute analytically the Lagrangian matrix of your dynamic model. Now, let's come back, let's pause this result for a while and let's see how we can leverage it for the general variable strain case. So once again, our job is to compute the Lagrangian matrix of the dynamic model, and we seek doing that using a Gaussian quadrature scheme. I think it's the most natural idea one can have. But to do so, we need the value of the configuration Jacobian and derivative of the Jacobian at the Gaussian point. For instance, in this example, you can see 3 Gaussian points. We need to compute those values there in order to integrate for those matrices. So now the question is how to get this value at the Gaussian quadrature point. So what we observe is that in each of those interval between two consecutive Gauss points, you can approximate the Magnus expansion using the Zanna collocation approach, which is another nice geometric result that we can find in a dedicated book. For instance, here I report a 4-order approximation of the Magnus expansion. You can have any order you want. So in a 4-order approximation, you need only 2 values of the strain in the interval of interest. Okay, once we have this Magnus expansion approximated, you can first of all compute the configuration of the cross-section and the rigid body of your system recursively employing the exponential map. Now let's move to, again, differential kinematics, how to compute the Jacobian and its derivative. So what the key observation now is that the quantity omega over h, where omega is the approximated Magnus expansion and h is the length of the interval between two quadrature points, this quantity behaves as a constant strain. So we can apply the analytic formula we have seen before. To do so, we also need to take the derivative of the Magnus expansion. For instance, again, this is a 4-order example. And now we can directly apply in each of those intervals, we can apply the analytic formula I showed you before that involved the tangent operator of the exponential map and its time derivative. Now, this relative velocity and the relative acceleration are relative with respect to the previous point. So once again, we can sum the relative velocity and the relative acceleration all along the chain, which produce a recursive formula for the Jacobian and the time derivative. So in conclusion, we propose a 2-level nested quadrature scheme to compute all the Lagrangian matrix of the aerodynamic model. It should be noted that this approach is different than a piecewise constant strain approach because we do not employ a different set of constant strain for each interval, but we have a single set of generalized coordinate for the entire link, and we just need to pick up the value that we need in order to build a localized constant strain model. Okay, let's now see some numerical test and example of this approach. So our first example is a cantilever beam with 100 meter long. So we try to stress our model. Here we are using 6 degrees of freedom, so 6 bending strain and a tip follower force from 0 to 9,000 Newton. We solve the static equilibrium and we find that the trace of the tip on the plane is exactly the same that you obtain with a geometrically exact finite element method, but with much less degrees of freedom, only 6 here. To do that with a finite element, you really need a lot of nodes. In this second example, we just let a cantilever beam, undamped cantilever beam, fall in gravity with only 4 degrees of freedom, so 4 bending mode. So being an undamped beam, we expect to have conservation in energy, and indeed we see that our computational approach and our model have a perfect conservation of energy, which show a robustness of the numerical scheme. Now some additional example. Here you see a classical cable-driven manipulator where subject to gravity as well, where the cable has this weird path inside of the manipulator. And we control the tension of the cable from 0 to few hundreds Newton. In this other example, we test how the model is good in modeling hybrid soft rigid chain. Here we have a rigid link connected to the ground by a revolute joint and a soft link connected to the rigid link by a spherical joint. And here we are controlling the motion of the revolute joint to be constant angular velocity. In this last example, we model an underwater soft vehicle composed by several rigid and soft parts. Again, we are controlling the motor, this small dark block, to rotate at constant angular velocity. Finally, my student E-class Ben Himdat prepared some tutorial in the posted session. Because we developed actually a matter toolbox out of this approach, and you can find a small tutorial there where E-class will show you how to set up the parameter of the link, how to build a linkage, and how to select, for instance, the order of your bending and torsion and whatever degrees of freedom you want to activate here. And then several things: static analysis, dynamic analysis, etc. You can head to the poster session to see more. I hope maybe I have 5 minutes more. I feel quite isolated. I hope you are hearing me and everything is going fine.
We are still with you, Federico.
All right, thank you. Great, because I have only one small screen, so I'm not aware of anything else happening around me.
Good.
Okay, thanks. So if I have some more time, I will show you briefly an extension of this approach to nested rod system. And here this part of the presentation can be found in a recently published RAL paper. So first of all, let me set the problem here. So far, we have shown you how we can model trade-like actuation, such as embedded tendons, cable, or embedded McKibben actuators. For those kind of actuation, the mechanical property are not very important, or if they are, they're easy to address, while only geometric parameters are needed for modeling. While in nested rod actuation system, clearly you cannot avoid the mechanical property of the rod itself, right? So this is the case of multi-backbone, embedded SMA, and concentric tube robot. So in the rest of this presentation, I will show you some initial step towards the generalization of the geometric variable strain approach to concentric tube robots. So first of all, what is a concentric tube robot? It can be think as a collection of Cosserat rods, such that the inner tube configuration differ from its outer tube only by a single rotation theta around the tangent vector. So what we need to do in order to, in addition to the kinematic we have developed so far for a single Cosserat rod, we have some additional kinematic for the inner tubes related to this additional rotation. So once again, we define the relative velocity and relative strain by taking the time derivative and space derivative of the additional degrees of freedom. Similarly, we equate the mixed partial derivative of the configuration, and we obtain the same transpositional relation as before, plus a new one, which is actually exact, as for the case of single-dimensional rigid link. Again, because it's single-dimensional, is a single degrees of freedom motion. So the transpositional relation is exact. For the continuous field, we once again parameterize them and discretize them by a finite set of strain mode. Now we have 2 sets, one as before, plus another one for the additional degrees of freedom, which is still distributed. It's one-dimensional, but still distributed. But once again, we follow the same procedure. We include this discretization in the general differential kinematics, and we obtain exactly the same geometric Jacobian as before for the degrees of freedom of the external rod, plus an additional Jacobian, much more simple, again, because it's exact, for the rotational degrees of freedom of the inner tubes. So why we do all of this, and why we don't just model two rod as two rod? Because now we can project the free equilibrium using the Jacobian. And why we want to do that? We want to do that in order to eliminate the unknown constraint interaction force that the two tubes exchange. That's why all of this effort. So thanks to this minimal parametrization, the constraint force disappear from the system. And in the static case, here we're looking only at static, we obtain a system of algebraic equations that can be solved for the unknown. This, before I show you the example of a single overlapping section, now we have three overlapping section, but the procedure is exactly the same, and we obtain similar algebraic equation for each of the section. In this case, we've also compared with the shooting method, which is very well known, especially in the medical community. And we have observed very good comparison with respect to the tip position. Then we have extended the modeling also to the transmission section. All of this system has an operational part and a transmission part, usually straight, but not necessarily, that live before the insertion point. So once again, we are able to model this part as well. Also, I would like to point out that we are able to include the sharp discontinuity in the parameter, in whatever of the system, just by subdividing again the section in multiple subsections. For instance, here, due to the transmissional part, we need to take another section where, when the straight configuration, sorry, the straight reference configuration of the inner tube finished, right? Again, we compare with the shooting method and we obtain very good result. Now, surprisingly, a very important phenomena that has been so far never included in the concentric tube robot model is what is called the spaghetti problem, which is very nicely represented by this Disney character, which arise when you have sliding beam. So what's the problem here is that during sliding, the domain of each of the section change. So you have a shrinking or a growing of the domain, which is not elongation. It's shrinking is the entire physical domain that change due to your input, which I call here D. So in order to account for this, we need to augment our kinematics with some additional term that take care of this change in the domain itself. So once you account this phenomena in a sliding, in a static setting, it allows you to compute to have a model for the insertion force and motion, which is actually has been not developed before. Okay, so in conclusion, I've presented a geometric variable strain approach for floating soft rigid system. The resulting model has a typical Lagrangian form, which is useful for analysis, control, and also simulation. We propose a two-level nested quadrature scheme to compute the Lagrangian metrics of the model, and we also start extending this approach to a concentric tube robot, which is a special case of nesting rod system. And also we start addressing the sliding rod problem that was not addressed before. Let me acknowledge some collaborators that are behind this presentation. Anup Matthew, Iklas Ben-Mida from California University, and Frédéric Boyer from EMT Atlantic. And thank you for listening.
And thank you, Federico, for this very detailed description of your approach. I think that really helped in understanding it. And Cosimo immediately put his hand up when he saw conclusions. So I hand over to you.
Okay, yeah, thank you. And thank you, Federico, for the great presentation. Ciao, Federico. So it's, I typed in the chat some questions, but maybe you can answer to them later because they are a bit more technical.
Sure.
But what I am curious about is to ask you another more general question. So you, with your framework, you start with an exact model technique, and then at some point you start introducing some approximation, like if I correctly understood, in the manual expansion, and then in the integral, to solving the integrals and so on and so forth. So my question is, you end up with something which is no more exact, and the question is, in which extent it pays off to start with something as complex as the exact formulation, if you then you have at some point to start introducing approximation.
So for me, the exact formulation is there to guarantee what is called this geometrically exact approach, right? So starting from there, you are sure that at least at that level, everything is what is called geometrically exact. And you have also a full picture from which you can take different direction. I propose one, but maybe you can take another one. And at that level, I really enjoy, from my point of view, the unification, if you want, between a rigid link and a soft one, which I think it's a good way, which doesn't introduce any approximation at that level, and is a good way to see the problem, and in order to then put equation behind it. Then the discretization, whenever you want to solve almost anything, right? There are very, very few examples out of the linear world that you can solve analytical, very, very, very few. In the planar case, there are there, for instance, with some Euler-Bernoulli approach, and Nabil Seaman it's quite an expert there, and others with the elliptic integral and so on. But I don't think we can really push that too much. Of course, so we introduce discretization and simplification, which discretization means approximation. However, if this kind of discretization is quite general, because, for instance, if your system end up to be constant curvature, for instance, the constant curvature approximation is not an approximation anymore. If your system end up to be quadratic strain, if you put a quadratic strain approximation, it's not approximation anymore. So it depends on the loading condition, on the operational condition. I think what I would like to do in the future is to find some clever way to select those bases depending on the geometry of your actuation, the geometry of your sensor, the kind of, or maybe running some simulation to more or less understand which kind of motion the system goes on, which is very typical actually of reduced order modeling, we can say, right? So as long as your reduced model catch up enough stuff of the global one, you are in a good shape.
Thank you.
Thank you very much, Federico. The question from Caspar, and I think then we should move on in the interest of time.
Yeah, maybe Darwin wants to also ask a question. I don't know, he switched on his video. Anyway, I go quick. Fantastic talk, I think, as well, especially if we want to consider using soft robots for medical applications. I think very useful. So my main questions are, how successful are you in modeling external forces? And have you actually validated that? So have you compared that with a real system?
So I will start with the second question about validation. We have in several papers validated the model in several instances. So we have some validation for the constant strain approach, which again depend how many sections you make, and you can reach the level of precision that you need. And also with Frédéric Boyer, and then we have, of course, some experiment, but I believe that it's easier to validate with experiment than to validate with other model, especially geometrically exact finite element method. So there is this big community which produce very incredible model that are very precise, and we try to validate with them. I present one example here. Frédéric has done other work in another recent paper. So yes, there is some validation. More has to be done. I think I see it as a, let's say, continuous validation, let's say, also because then you can change the computational approach, so you need to validate again and so on. It's still very, very, many things to be explored. For what concerns external force, I see it as a problem in physics more than mechanics. So when the external force are constrained force, you can use geometry, and then you can have, you don't need physics. But otherwise, for instance, in the fluid, at least in my approach, I don't simulate all the particles of the fluid. We use simplified parameters model that have to be identified. I will do the same for friction and stuff like that. Gravity, of course, you can put it there, and other kind of potential force you can put there. But otherwise, I see it either you go on to the physics if you need it, or you try to do some parameter model.
Thank you. Thanks a lot.
Thank you very much, Kaspar.
Thank you. Davin, did you have one, or?
No, it's okay. I can leave for later. I can leave. It's fine.
Thank you. So thank you very much, Federico, for presenting your work. And I think if we can all unmute before we go to the award session, and thank all the speakers for today for presenting their fantastic work. So a big applause for them. So now there was in parallel a poster session that happened, and as part of this workshop. I hope you can see on my screen. So throughout these 3 days, there were several posters that were uploaded, including their videos on the website that you can see here. And in fact, we have also an award that we dedicated to the best poster. And I would like for the panel to come forward to present these. So I think the first one will be, or the part of the award announcement, maybe I can ask Panos to speak about how this has been done and what the final decision was.
Yes, thank you, Helge. So we had 10 posters in total submitted, and we asked our speakers that had not submitted a poster to vote for their best posters and to mark the posters. And what happened was that we got a tie. So we got 3 posters tying on first place. So we ended up deciding to split the award between all these 3 winners. And I'm pleased to announce that the first of these the 3 winners on first place is the development for a real-time augmented reality robot-patient platform with haptic feedback using a 3D surrogate model. The first author being Florence Leong from Imperial College London. And yes, Helge, over to you.
So many congratulations to Florence. I'm sure that the organizers of this workshop will be in contact with you after the workshop. So the second paper that we believe is on the same deserves the win is bringing light to the insertion of cochlear implants using tetrapolar bioimpedance measurements. And here the first author is Daniel Bautista Salinas from Imperial College London.
Congratulations, yeah, also from me to all of them. And I have now the pleasure to announce the third winner, but also third joint winner, so same level as the other two. And yeah, here we are. It is soft multimodal sensor with adjustable force sensing range for soft tissue palpation. And the first author is Duncan Reid. So congratulations also to that team. Congratulations.
So this leaves me to thank everyone who was involved in organizing this workshop. Marianne Knight, who is working always in the background, and without her help, I'm sure that these events would not be as smooth as this. So thank you very much, Marianne. At the same time, all the speakers from all days, from around the world, it is a pleasure and very, we feel very precious to have you within these workshops, that you share your work with us, and of course the panel members, Panos, Anne, Kasper. Thank you very much for chairing the sessions and organizing this workshop.
Thanks also to Helge, of course, and the audience. Thanks a lot for joining us.
See you next time.
Thank you very much.
Thank you.
See you.
Thank you very much. Bye-bye.
Bye-bye.
Bye.